Board, China may have just moved one of the most important parts of artificial intelligence hardware away from organic circuit boards and toward glass. BOE, the Chinese company best known for display panels, says it has completed a large, high-layer count glass core substrate sample for advanced chip packaging. The structure uses a 929 build with 20 board total layers. More importantly, BOE says the sample passed demanding reliability tests, including 1,000 thermal compression bonding cycles, moisture tests, high-temperature storage, low-temperature storage, and preconditioning. That does not mean China has mass-produced a finished glass AI processor. It does not mean silicon has disappeared. And board, it does not mean every copper connection inside a computer is about to vanish. But it does mean glass packaging is moving from concept demonstrations toward hardware that can survive the stresses expected in manufacturing and operation. BOE is also forming a dedicated team to develop micro-LED optical interconnects and glass substrate co-packaged. Board optics. The future bottleneck inside AI systems may not be computing power. It may be the copper wiring, carrying data between processors, memory, and network devices. If glass substrates can support larger packages, finer wiring, better dimensional stability, and optical links placed closer to chips, they could change how future AI computers are. Board assembled. So has China built a 20-layer glass AI chip that could end copper, but it may have passed one of the tests required to make that possibility serious. What Bo actually built. A modern AI accelerator is not simply one small silicon rectangle. The finished product can include multiple computing dies, high-bandwidth memory stacks, delivery board, components, controllers, and communication links. These parts must be positioned, powered, cooled, and connected with extraordinary precision. The structure supporting them is called a package substrate. It sits between the silicon devices and the larger system board, carrying power and signals across thousands of tiny electrical connections. Most advanced substrates today use organic materials, but as packages grow larger and wiring becomes denser, organic substrates face physical limitations. They can expand, shrink, bend, or warp during heating and cooling. Even tiny dimensional changes matter when engineers align extremely fine connections across a package containing many chiplets. Board glass offers a different foundation. It can remain flatter across large areas, provide strong dimensional stability, support very fine features, and offer useful electrical properties for high-speed signals. BOE says its 20-layer sample uses a 9-to-9 configuration. In simple terms, that means 9 build-up layers on one side, a central 2-layer board glass core section, and another 9 build-up layers on the opposite side. The design matters because advanced packages need many routing layers to distribute power and connect processors, memory, and external interfaces. Building a large 20-layer substrate that remains aligned and reliable is much harder. Why the reliability test matters. Using board hardware repeatedly heats during operation and cools when workloads stop. Different materials expand at different rates. That creates stress around copper vias, solder joints, wiring layers, and interfaces. High temperatures can weaken materials, while low temperatures can create contraction and cracking. Manufacturing steps such as bonding add board pressure and heat before the package reaches a customer. BOE says its samples passed several industry reliability tests was thermal compression bonding cycling reported at 1 cycles. Thermal compression bonding uses controlled heat and pressure to create fine electrical connections. Repeated cycling helps reveal whether interfaces separate, crack, or board lose electrical performance under stress. The sample also reportedly passed accelerated temperature and humidity testing, biased humidity testing, high temperature storage, low temperature storage, and preconditioning. These tests do not prove the substrate will survive every product, factory process, or operating environment. The company is board testing whether a complex multi-layer structure can remain functional after repeated environmental and manufacturing stress. That is essential before chip companies will trust a new substrate beneath expensive processors and memory. Why AI packages keep getting bigger. One package may contain several compute dies and multiple stacks of board high bandwidth memory. A single piece of silicon cannot grow forever. Manufacturing defects become more expensive as die size increases, while practical size is limited by lithography equipment. Chip makers therefore divide large designs into smaller chiplets and connect them inside one package. But it moves a major engineering challenge from the board silicon die into the package. The substrate must connect many devices with enough bandwidth that they behave like one system. It must remain flat enough for thousands of fine connections to align correctly, and it must support larger physical dimensions without warping. Glass is attractive because it can potentially support larger package formats. Board, then organic materials, while maintaining tighter dimensional control. That does not make glass automatically cheaper or easier. Drilling and filling extremely small vertical holes is difficult. Cutting large glass panels without damaging stress is also challenging. BOE says it developed capabilities including high aspect ratio through glass via board formation, deep hole copper filling, low stress metallization, multi-layer lamination, high density routing, and low stress cutting. Those processes turn plain glass into a usable electronic platform. The copper bottleneck, the title says, copper may be finished. Copper is not disappearing from electronics. Even BOE's glass substrate relies on board copper-filled vias and metal wiring. Power delivery will still require conductive paths, and short electrical connections will remain essential. The real problem is distance and bandwidth. As data rates increase, copper links consume more energy and become harder to operate reliably across longer paths. Electrical signals lose strength, generate board heat, interfere with nearby channels, and require increasingly complex equalization. Inside a large AI system, processors and memory must move enormous quantities of data every second. Engineers can improve copper, but the energy cost per transmitted bit is becoming a concern. Optical communication sends information using light. Light can move board large amounts of data with lower loss across distance and reduced electromagnetic interference. The industry already uses optical transceivers for many network links. The next step is bringing optical components much closer to the processor. That idea is called co-packaged optics. Instead of sending high-speed electrical signals from a chip across board, a long board, to a separate optical module, optical engines are placed near or inside the main package. The electrical path becomes shorter. This can reduce power consumption and support higher bandwidth. Why glass and optics fit together? Glass is interesting for optical integration. It is dimensionally stable, can support precise structures, and board can provide a platform for electrical routing and optical components. BOE says it formed a project team focused on micro-optical interconnect systems and glass substrate co-packaged optics. Micro-LEDs are extremely small, light-emitting devices. They are best known as display technology, but their size and fast response make them candidates. Board for short-distance optical communication. A micro-LED array could potentially transmit many optical channels in parallel across short distances that could help AI servers move enormous bandwidth between nearby devices while minimizing power. BOE has decades of experience processing large glass panels and developing display technologies, including board micro-LED manufacturing. The company is trying to reuse those capabilities in semiconductor packaging and optical interconnects. Display manufacturing and advanced chip packaging have different tolerances, materials, customers, and reliability demands, but BOE already understands large area glass processing, precision patterning, multi-layer board structures, and mass production automation. From display factory to chip packaging, BOE's move is part of a larger shift. Display manufacturers built factories capable of processing large glass panels with fine patterns, thin films, and precise alignment. Advanced semiconductor packaging is one of those markets. BOE brought a glass core substrate board pilot line online with a design capacity of roughly 1,000 substrates per month. The company says it delivered samples to domestic customers. Some customers reportedly completed concept verification and entered technical testing. However, BOE also says the business has not reached mass production and has not generated mass production revenue. That board distinction matters. A pilot line proves samples can be produced repeatedly. It does not prove competitive yield, cost, throughput, or customer adoption. For a commercial AI package, every substrate must meet strict specifications. A small defect can ruin a product containing extremely expensive processors and memory. The challenge is not board producing one successful piece. It is producing thousands with consistent quality at a price customers will accept. The global glass race, China is not alone in pursuing glass substrates. Intel has spent years researching glass core packaging. Other substrate makers, equipment companies, foundries, and display manufacturers are also developing board glass processes. The attraction is global because every major AI chip company wants more memory bandwidth, more chiplets, larger packages, lower power, and faster interconnects. Glass is one possible solution, not the only one. Organic substrates continue improving. Interposers remain important for extremely dense connections, fan-out packaging, board, advanced bridges, and new redistribution technologies are also evolving. The winning architecture may combine several materials rather than replacing everything with glass. China's significance comes from manufacturing scale. If BOE adapts large panel glass processing to semiconductor requirements, it could build substrates using panel-level board methods rather than treating every package like a small wafer. Panel processing may increase the number of large substrates produced per cycle. But larger panels also create more opportunities for defects, alignment errors, stress, and breakage. The economic advantage exists only if yields become high enough, what the 20-layer result does not. Board prove the reliability milestone is important, but several things remain unproven. BOE has not announced a commercial AI accelerator shipping on this substrate. It has not disclosed the customer final package design production yield, selling price, or long-field reliability. The company has not shown that its glass substrate is superior to every board competing organic, silicon, or glass solution. Its optical interconnect project is still under development. A dedicated team is not the same as a finished co-packaged optics product. The phrase copper may be finished should be understood as a direction, not a completed transition. Copper links are reaching limits in the highest bandwidth parts of board AI systems. Optics may gradually replace longer, faster electrical connections, but copper will remain inside packages, boards, power systems, and many short-reach links. The likely future is hybrid. Electricity will deliver power. Copper will handle many local connections. Optical links will move increasing amounts of data where electrical board transmission becomes inefficient. Glass could become the platform allowing those technologies to coexist inside one large package. Why this matters for China. Advanced packaging is strategically important because computing performance no longer depends only on manufacturing the smallest transistor. A company can combine chips, memory stacks, and board optical links to create a powerful system, even when individual dies use different process nodes. Packaging does not erase the value of leading-edge fabrication. It gives engineers another path to improve performance. China faces restrictions on advanced semiconductor equipment and high-end AI hardware that creates pressure to improve every part. Board of the domestic computing stack. Glass substrates, panel-level packaging, optical interconnects, domestic memory, and chiplet integration can help China extract more performance from available chips. BOE represents a different type of semiconductor competitor. It is entering through glass, displays, micro-LEDs, and large-scale panel manufacturing. Board, rather than a traditional foundry, that cross-industry approach could create new options if conventional substrate suppliers cannot scale quickly enough for AI demand. My take is that BOE's 20-layer reliability result is meaningful, but the headline should not be mistaken for a finished revolution. China has not replaced silicon with board glass, BOE has not eliminated copper, and a pilot line producing customer samples is not a mature commercial supply chain. What BOE has done is more specific. It built a large, complex glass core substrate, developed processes to route signals and power through it, and pushed the sample through serious reliability testing. At the same time, it is board connecting that glass strategy to micro-LED optical interconnects and co-packaged optics. That combination matters because future AI systems need larger packages and faster, more efficient communication. Glass may help solve the mechanical problem. Optics may help solve the bandwidth problem. If BOE combines them economically, China could become board an important supplier of the platform beneath future AI chips, even without manufacturing the processors themselves. The next test is not another laboratory record. It is customer qualification, production yield, cost, and deployment inside a real computing product. So, what do you think? Will glass substrates and optical links become the board foundation of future AI hardware, or will manufacturing complexity keep organic packages and copper connections dominant? Let me know your view in the comments and subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the race for AI leadership is no longer board happening only inside the transistor. It is also happening beneath the chip, between the memory and across every connection, carrying the board data